At some point in the past, the entire universe fit inside something smaller than an atom, not metaphorically, mathematically. And when physicists try to describe what was happening in that moment, both of their greatest theories, the two frameworks that explain literally everything else in existence, produce the same answer: gibberish. Not approximately wrong, completely, catastrophically broken. Today we are going to walk right up to that moment together. We are going to look at the wall that sits at the beginning of time, understand why nothing in physics can see past it, and ask the question that keeps certain cosmologists awake at night. Is there actually a past tense to the universe at all? Stay with me. This one will melt your brain. If you are new here, welcome to Sundown Science. Hit subscribe, pour something warm, and get comfortable. Because tonight we are going to find the wall, the actual place where human knowledge stops, and then we are going to stand there and stare at what is on the other side. Now, settle in, and let's ease into this one slowly. Part 1. The instant everything breaks. There is a moment in the history of the universe so brief that if you tried to count it out loud, the entire lifespan of every star that has ever burned, every galaxy that has ever spun, every atom that has ever existed would be over before your lips even formed the first syllable. 10 to the negative 43 seconds. That is not a small number in the way that a grain of sand is small, or in the way that a bacterium is small. That is a number so far outside the range of human experience that the only honest thing to say about it is this: your brain was never built to understand it. And yet, tucked inside that sliver of time is the single most important event in the history of everything. And physics cannot tell you what happened there. Not because we haven't tried, not because the instruments aren't sensitive enough, but because the laws of physics themselves walk up to that moment, look directly into it, and fall apart completely. Let us rewind. Not metaphorically. Let us actually think through what it means to run the universe backward. You take everything, every planet, every star, every black hole, every photon of light currently crossing the space between galaxies, every atom in your body, every neutrino passing through the floor beneath you right now without even slowing down. You take all of it and you compress it. You run the expansion of space in reverse. Galaxies that are currently racing away from each other begin to approach. The space between them shrinks. Matter grows denser. Temperature climbs. Radiation intensifies. You keep going. The large-scale structures dissolve. The filaments and voids that give the universe its texture at the largest scales collapse inward. Galaxies merge. Stars dissolve into plasma. Atomic nuclei break apart under the heat. Protons and neutrons come undone into their constituent quarks. The universe gets hotter and smaller and denser with every fraction of a second you rewind. And then, somewhere around 10 to the negative 32 seconds after what we call the Big Bang, inflation ends, and you are in a regime where the known physics of the standard model is being pushed toward its limits. Keep going, push further back. 10 to the negative 12 seconds, the Higgs field has just switched on, giving particles their mass. 10 to the negative 35 seconds, grand unification energies, where the strong force and the electroweak force may have been a single, unified interaction. The universe is now smaller than a proton. Keep going, push harder. The temperature is now so extreme that the energy of every particle in the universe is approaching something almost unimaginable. And then you reach it. 10 to the negative 43 seconds, the Planck Epoch. And everything breaks. Not dramatically, not with a flash or an explosion. The equations just stop working. General Relativity, Albert Einstein's magnificent description of gravity as the curvature of space-time, extrapolates backward to a singularity, a point of infinite density, infinite curvature, infinite temperature. And in physics, whenever you get an infinity in your answer, that is not a result. That is your theory waving a white flag. An infinity in a physical equation does not mean the universe was actually infinite in density. It means your theory has been pushed beyond the domain where it applies. The math breaks down. Einstein's equations, which have successfully described the motion of planets, the bending of light around stars, the existence and behavior of black holes, the expansion of the universe itself, those equations hit the Planck Epoch and produce nonsense. They produce infinity. An infinity is not a physical answer. Now here is where it gets genuinely strange, because you might think the solution is simply to switch theories. General relativity fails at extreme density? Fine, use quantum mechanics instead. Quantum mechanics is the other pillar of modern physics, the framework that describes how matter and energy behave at the smallest scales. It has been tested to extraordinary precision. Its predictions match experiment to more decimal places than almost any measurement in science. Quantum mechanics should, in principle, be able to handle the conditions of the very early universe, except it cannot. Because quantum mechanics has its own problem at the Planck Epoch, and the problem is almost philosophically poetic in how perfectly it contradicts relativity, quantum mechanics, at its foundation, is built on the Heisenberg uncertainty principle. The more precisely you know the position of a particle, the less precisely you can know its momentum. The more tightly you confine something in space, the more wildly its energy fluctuates. Squeezing things into smaller and smaller regions does not produce calm, well-defined points of infinite density. It produces violent, probabilistic smears of energy that refuse to be pinned down. Quantum mechanics says you cannot have a singularity. You cannot have a point of infinite precision. The universe, according to quantum mechanics, is fundamentally granular and uncertain at the smallest scales. So here you have two theories. General relativity says the early universe collapses to a singularity, a point of perfect, precise, infinite density. Quantum mechanics says no point in the universe can ever be perfectly precise. These two statements are not in tension. They are not slightly uncomfortable neighbors who avoid eye contact. They are direct, irreconcilable contradictions. And both theories are, in their respective domains, extraordinarily successful. General relativity correctly predicted gravitational waves a century before we detected them. Quantum mechanics correctly predicts the behavior of transistors, lasers, chemical bonds, and the structure of matter itself. These are not failed theories. These are the two most tested, most verified, most successful theories in the history of science, and they are mutually incompatible at the Planck Epoch. That is the wall. That is what we are dealing with. Now, let us be precise about what the Planck time actually is, because it is important to understand that 10 to the negative 43 seconds is not a number someone chose arbitrarily. It is not a convention. It is not a cutoff that physicists agreed on at a conference. It is derived, inevitably, mathematically, necessarily, from three of the most fundamental constants in nature. The speed of light, which is approximately 299,792,458 meters per second, the gravitational constant, which determines the strength of gravity, and the reduced Planck constant, which governs the scale at which quantum effects become significant. When you combine these three constants in the unique way that produces a unit of time, you get the Planck time. There is only one combination. There is no choice involved. The universe's own laws, when asked to define their own limits, point to this number. 10 to the negative 43 seconds is not where physicists decided physics stops working. It is where physics itself declares its own boundary. To give you some sense of scale, and this is important because the numbers involved are so extreme that they become meaningless without context, consider the following comparison. A proton is roughly 10 to the negative 15 meters across. A galaxy, say our own Milky Way, is roughly 10 to the positive 21 meters across. The ratio between a proton and a galaxy is therefore roughly 10 to the 36. That is the difference between the smallest structure in ordinary matter and a structure containing hundreds of billions of stars. Now consider that the Planck length, the spatial equivalent of the Planck time, the smallest meaningful length scale in physics, is 10 to the negative 35 meters. That means the ratio of a proton to the Planck length is roughly 10 to the 20. A proton is to the Planck length as a galaxy is to something larger than our observable universe. The Planck scale is not small in the way that atoms are small. It is small in a way that makes atoms look like superclusters, and the entire cosmic history of the universe, every event that has ever occurred, every star that has ever formed, every living thing that has ever drawn breath, is the downstream consequence of whatever happened in a region smaller than that, at a time earlier than that. Everything you see when you look up at the sky passed through the Planck Epoch. Every atom in your body passed through it, and we have no description of what that was. This is the thing that deserves to sit with you for a moment. We tend to talk about the Big Bang as the beginning of the universe, the starting gun, the first event, the moment it all switched on. But the more precise and honest framing is this: the Big Bang is not where the universe began. The Big Bang is where our physics stopped working backward. The singularity at the end of General Relativity's backward extrapolation is not a physical object or a physical moment. It is the location where the theory breaks. It is the point past which the map has no more detail. And whether there is something on the other side of that boundary, whether the universe had a genuine first moment, or whether it extends in some form we cannot currently describe into what we naively call before, is a question we cannot answer, not yet, maybe not ever. Einstein himself was uncomfortable with singularities. He believed, late in his life, that the appearance of infinities in physical theories was always a sign that the theory was incomplete, rather than a sign that the universe was actually infinite in any physical sense. He was probably right. The singularity at the heart of the Big Bang is almost certainly not a real physical object. It is almost certainly a signal that our theories need to be replaced by something deeper, a theory of quantum gravity that can describe the behavior of space-time itself at the scales where quantum effects and gravitational effects are both simultaneously important. We do not have that theory. Several candidates exist, and we will examine them. But for now, what matters is this: the universe begins, as far as our physics is concerned, as a paradox, not as an event, as a collision between two incompatible descriptions of reality, both correct in their domains, both shattered at this single boundary. The universe did not start with a bang, it started with a contradiction. And that contradiction is what we are going to spend the next several hours unpacking. There is something else worth pausing on here, something that will become more important as we go further into this. We said that time itself may lose meaning at the Planck Epoch. That is not a poetic statement. It is a serious claim that follows from the physics. In general relativity, time is not a fixed background against which events happen. Time is part of space-time, a geometric structure that is shaped by mass and energy, that can curve and stretch and in extreme circumstances become distorted in ways that have no classical analogue. At the Planck Epoch, space-time itself, including the time dimension, is being subjected to conditions so extreme that its smooth, geometric structure almost certainly breaks down. If space-time is not smooth, if geometry is not well defined, then the very concept of a before and after, the concept of one event following another, of causation flowing in a direction, may not apply. The Planck Epoch is not just a moment we cannot see into clearly. It may be a region where the concept of a moment stops making sense entirely. What lies on the other side of that wall may not be describable in terms of time at all. And if there is no time, there is no before the Big Bang in any meaningful sense. There is just the boundary, the wall, and whatever is on the other side of it, which may be something for which we have no language and no concept yet developed. That is where we are going, and we are only just getting started. Part 2. The wall hidden inside the laws of physics. Max Planck did not set out to define the limits of the universe. In 1899, he was working on a problem that, by the standards of cosmological questions, seems almost mundane: the spectrum of radiation emitted by a hot object. It was a well-known puzzle in theoretical physics at the time, the so-called black-body radiation problem, and Planck's solution to it introduced something he himself called a purely formal assumption: the idea that energy is not continuous, but comes in discrete packets, or quanta. He found this result deeply uncomfortable. He spent years trying to find a way around it. He could not, and in the process, he introduced the constant that now bears his name, the reduced Planck constant, the fundamental quantum of action, and with it, something he noticed almost as a footnote. You could combine the Planck constant with Newton's gravitational constant and the speed of light to produce a set of natural units, units of length, time, mass, and temperature, that were not based on any human convention. Not on the meter, which is defined relative to the size of the Earth. Not on the second, which is defined relative to the rotation of the Earth. These were units derived purely from the fundamental constants of nature. Planck called them natural units. He noted, somewhat prophetically, that they would retain their meaning for all time and for all civilizations across the universe. He was right, and he had no idea what he had actually found. What Planck had stumbled across was something more profound than a convenient unit system. He had found the universe's own internal scale for its own limits. When you combine the gravitational constant, the speed of light, and the Planck constant, the Planck length that emerges is approximately 1.6 times 10 to the negative 35 meters. The Planck time, the time it takes light to travel one Planck length, is approximately 5.4 times 10 to the negative 44 seconds. The Planck mass, the mass concentrated in a Planck-sized region that would make it a black hole, is approximately 2.2 times 10 to the negative 8 kilograms. These are not small numbers in a cosmological sense. The Planck mass, remarkably, is about the mass of a flea's egg. It is visible to the naked eye, at least in principle. What is extraordinary is not that these numbers are large or small in an absolute sense. What is extraordinary is where they come from and what they signify. They are the scales at which the two great pillars of physics, quantum mechanics and general relativity, become simultaneously important. They are the scales at which you cannot ignore gravity when doing quantum mechanics, and you cannot ignore quantum mechanics when doing gravity. They are the scales at which everything we know about physics intersects and breaks. Here is a way to understand why those two scales intersecting is so significant. In quantum mechanics, there is a quantity called the de Broglie wavelength, the quantum mechanical wavelength associated with a particle. The more energy a particle has, the shorter its wavelength, which is why particle accelerators use higher and higher energies to probe smaller and smaller scales. You want to see detail at small scales? You need short wavelength probes. Short wavelength probes require high energy. This is fundamental. Now, in general relativity, any sufficiently dense concentration of energy will curve spacetime so severely that it collapses into a black hole. The boundary at which this happens is called the Schwarzschild radius, the radius at which the escape velocity from a mass equals the speed of light. So here is the problem. You want to probe a very small region of space. You need a high-energy particle with a very short wavelength. But as you increase the energy to shorten the wavelength, the energy concentration in that small region grows. At some point, the energy concentration becomes so extreme that the Schwarzschild radius of your probe, the radius at which it would collapse into a black hole, equals its own quantum wavelength. Your measurement apparatus destroys the thing you are trying to measure, not because of a technical limitation, not because you need better engineering, but because the act of observation, at sufficient precision, creates a black hole. Observation becomes catastrophically destructive. The universe, quite literally, will not allow you to probe below the Planck scale. This is not a human limitation. This is a structural feature of the laws of physics themselves. This is what makes the Planck wall so different from other limits in science. The sound barrier was a technological barrier overcome by better engineering. The limit of the naked eye was a practical barrier overcome by telescopes and microscopes. Even the speed of light, while an absolute barrier to travel, does not prevent us from observing things that move at those speeds. But the Planck scale is different in kind, not just degree. It is a self-referential barrier, one that emerges not from our limitations as observers, but from the internal structure of the laws themselves. The universe's rules, applied to their own measurement, produce a wall. You cannot get around it by building a bigger accelerator or a more sensitive detector. You cannot get around it because the act of trying to look causes the thing you are looking at to vanish behind an event horizon. The wall is not hiding something. The wall is part of the structure of reality itself. Or at least, that is one interpretation. There are others. And the question of which interpretation is correct is one of the deepest open questions in all of physics. It is worth sitting with the strangeness of what has just been said. The laws of physics, from three fundamental constants, the gravitational constant, the speed of light, and the quantum of action, generate their own boundary condition. Without any external input, without any assumption about cosmology or initial conditions, the equations themselves produce a scale below which they cannot be applied. This is remarkable. Most theories in physics break down because they are approximations of something deeper. Newtonian mechanics is an approximation of relativistic mechanics, which is an approximation of quantum field theory. Each breakdown points toward a more fundamental layer. But the Planck scale is different. It is not the breakdown of one approximation in favor of a better one. It is the breakdown of both of our deepest theories simultaneously. It is the scale at which we need not just a refinement, but a revolution, something genuinely new, something that does not yet exist in complete form, to describe what is happening. The wall we cannot see past is not a wall between two different theories. It is a wall between our current physics and whatever deeper physics lies beneath. And this is what makes the opening question, is this wall a doorway or an edge, so genuinely hard to answer. A doorway would mean something is on the other side, something physical, something describable, something that a future theory of quantum gravity will eventually illuminate. An edge would mean this is it, this is the bottom of the stack. There is no before the Planck epoch, no deeper layer, no further description to be found. The universe simply begins here, at this boundary, and asking what came before is like asking what is north of the North Pole. The question sounds meaningful but refers to nothing. We do not know which of these is true. The universe has not told us. And the reason it has not told us is the same reason we cannot probe below the Planck scale directly. The wall itself prevents the very observations that would answer the question. Consider what this means for our understanding of the Big Bang. We speak about the Big Bang with a confidence that is somewhat misleading. We know a great deal about the universe from about 1 second after the Big Bang onward. The predictions of Big Bang nucleosynthesis, the formation of hydrogen, helium, and lithium in the first few minutes, match observations with extraordinary precision. The cosmic microwave background, the afterglow of the hot early universe that we can observe today, encodes information about the universe at roughly 380,000 years after the Big Bang, and its properties match theoretical predictions in exquisite detail. We have genuine, observationally grounded knowledge of the early universe, but this knowledge extrapolates back to a point, and that point is the Planck epoch. Before 10 to the negative 43 seconds, the math fails. The physical description breaks down. We are extrapolating our theories into a regime where they do not apply. The confidence with which we sometimes speak about the beginning of the universe papers over this fundamental gap. The Big Bang, as a theory, is extraordinarily well supported. The first instant of the Big Bang, the Planck Epoch, is completely uncharted. There is a phrase that will serve as a kind of anchor throughout this exploration, a phrase that captures the central strangeness of what we are dealing with. The universe has a wall we cannot see past. It is not hidden behind distance. It is not obscured by clouds of gas and dust. It is not simply too far away or too faint to detect. It is hidden behind a fundamental barrier built into the structure of physical law, a barrier that our two greatest theories, applied to the same problem, construct together by catastrophically failing at the same scale. Everything that has ever happened in the observable universe, every atom, every photon, every gravitational wave, every thought you have ever had exists on this side of that wall. And on the other side, we do not know. We are not even sure the question makes sense. But we are going to try to understand what that wall is made of, why it exists, and what it might mean that it does, because this is not an abstract puzzle for physicists to argue about in journals. This is the central mystery of existence itself. And the answers, whatever they turn out to be, will change everything about how we understand the universe we live in. Part 3. Why 10 to the negative 43 seconds is not arbitrary. There is a thought experiment that cuts to the heart of why the Planck time is not an arbitrary number, and it is one that begins with Heisenberg. You have probably encountered the uncertainty principle before, the idea that you cannot simultaneously know the exact position and the exact momentum of a particle. But it is worth understanding this not as a limitation of your measuring instruments, but as a fundamental feature of reality. The uncertainty principle does not say that particles have definite positions and momenta that we simply cannot measure simultaneously. It says that position and momentum, in a deep sense, do not both exist with definite values simultaneously. The universe is genuinely indeterminate at small scales. Now, here is where it becomes relevant to the Planck scale. The uncertainty principle has an energy-time version as well as the position-momentum version. It states that the more precisely you define the timing of an event, the more uncertain its energy content must be. Or, equivalently, a short burst of measurement necessarily involves large energy uncertainty. This might seem abstract. It becomes very concrete when you consider what happens as you try to probe shorter and shorter timescales. Suppose you want to measure what the universe is doing at some very short time interval. To resolve events at that timescale, you need to use probes, particles, radiation, whatever, whose own quantum uncertainty in time is smaller than the interval you are trying to resolve. By the energy-time uncertainty principle, this requires your probes to have very large energy. Very large energy in a small region means very large energy density. And here is where general relativity steps back in. Energy, in Einstein's framework, is equivalent to mass via E equals mc squared, and mass curves spacetime. Concentrate enough energy into a small enough region, and you do not just measure something, you curve spacetime so severely that you create a singularity, or at minimum, a region from which information cannot escape. You create a black hole. The very act of measuring at short enough timescales curves the spacetime you are trying to measure into an object that prevents measurement. At what timescale does this happen? The Planck time. Not approximately the Planck time. Exactly the Planck time, up to factors of order 1. You could not have chosen a different number. The physics determines it. This is the argument for why the Planck time is not a human convention, but a physical threshold. Below the Planck time, quantum uncertainty in energy is sufficient to curve spacetime into a black hole. Above the Planck time, you can, in principle, make measurements without destroying the thing being measured. The Planck time is the crossover. It is the exact scale at which quantum effects and gravitational effects become simultaneously important, and below which they are both simultaneously unignorable and mutually incompatible. This is why the Planck epoch is the boundary where physics fails, not because someone drew an arbitrary line, but because the two theories that constitute our best description of reality both become essential and both break at this exact scale for reasons that are mathematically inevitable. Now consider what this implies about spacetime itself below the Planck scale. In general relativity, spacetime is a smooth, continuous manifold, a geometric structure that can be curved by mass and energy, but which remains well-defined and smooth at all scales. You can always zoom in further. The fabric of spacetime, in Einstein's description, has no minimum resolution. It is smooth all the way down. But quantum mechanics challenges this picture in a profound way. If quantum uncertainty in energy at small timescales is sufficient to create black holes, then spacetime cannot be smooth at and below the Planck scale. The geometry must fluctuate. The very distances between points, the very topology of space, whether two regions are connected or separate, must be subject to quantum uncertainty. Spacetime cannot be a fixed background against which events happen. At the Planck scale, spacetime must itself be a quantum object, something that fluctuates, that is uncertain, that does not have a definite geometry at any given moment. This idea was first articulated in a serious way by John Archibald Wheeler in the 1950s. Wheeler, one of the most creative and influential physicists of the 20th century, introduced the concept of quantum foam, the idea that at the Planck scale, spacetime is not a smooth, continuous surface, but something more like the surface of the ocean, at a molecular level, turbulent, bubbling, foaming, with no stable geometry at the smallest scales. Wheeler imagined that at scales far below what any instrument could probe, space itself was constantly fluctuating, with wormholes, tunnels, connecting distant regions of spacetime, spontaneously forming and dissolving, with the topology of space itself changing from moment to moment. This was a radical proposal. Topology, the global structure of space, the question of how regions are connected, was, in classical physics, something fixed and unchanging. You cannot smoothly deform a sphere into a torus. A sphere and a torus are topologically distinct. Wheeler was suggesting that at the Planck scale, the universe does not respect this. Topology itself becomes uncertain. The question of how many holes space has, of how regions are connected, does not have a definite answer at the Planck scale. This is deeply counterintuitive. We are accustomed to thinking of space as the container in which things happen, the fixed stage on which the drama of physics is played out. Quantum mechanics tells us that particles do not have definite positions. Quantum mechanics tells us that energy comes in discrete packets. But surely space itself, the container, is fixed. Surely the stage does not participate in the drama. Wheeler was saying no. The stage participates. At the Planck scale, the stage is the drama. Space itself is quantum mechanical. Its geometry is not fixed. Its topology is not fixed. Distance, direction, connectivity, these concepts, which seem so fundamental to our experience of reality, are approximations that emerge at large scales from something more fundamental and more turbulent at the Planck scale. They are not the bottom of the stack. They are macroscopic features of a quantum geometry that is, at its smallest scales, almost unimaginably chaotic. Here is a way to think about this that may help. Consider the surface of the ocean. From an airplane, the ocean looks smooth. From a ship, you see large waves, but still a relatively coherent surface. From a small boat, the waves become more significant relative to the boat's size. In a swimming pool, you notice ripples and eddies. If you could zoom in to the molecular scale, you would see molecules of water bouncing randomly in all directions, with no smooth surface visible at all. The apparent smoothness of the ocean at large scales is a statistical average of an incredibly chaotic molecular reality. Wheeler was proposing that space-time is similar. At the scales of everyday experience, space-time is smooth and well described by general relativity. As you zoom in toward the Planck scale, it becomes increasingly turbulent. At the Planck scale itself, there is no smooth geometry remaining. There is just the quantum foam, a seething, fluctuating structure in which the concepts of distance and direction and connection lose their ordinary meanings. And here is why this matters for the wall we cannot see past. The Planck Epoch is not just a moment when conditions were extreme in a quantitative sense, hotter than we can measure, denser than we can probe. It is a moment when the very structure of space-time was almost certainly not smooth, not well-defined, not geometric in the ordinary sense. Our two great theories, general relativity and quantum mechanics, both presuppose a smooth space-time as the background against which they operate. General relativity describes how matter curves smooth space-time. Quantum mechanics describes how particles propagate through smooth space-time. At the Planck epoch, there was no smooth space-time. There was no fixed background. There was no stage. And without a stage, neither theory can operate. This is the deepest sense in which the Planck epoch is a wall. It is not just that conditions were extreme. It is that the precondition for our theories, the existence of a smooth background space-time, was almost certainly absent. We are trying to describe an epoch in which the very foundation of our description was not yet in place. The wall is not a wall around a room we cannot enter. The wall is the absence of the floor. Part 4. The universe before makes sense. One of the most disorienting things about the Planck epoch is what it does to the concept of time, not in a metaphorical sense, not in the sense that extreme conditions make the universe feel timeless. In a precise, mathematical, physically grounded sense, the concept of time as a well-defined ordering of events may simply not apply to the Planck epoch. This is a claim that needs to be unpacked carefully, because it is easy to hear it as poetic license and dismiss it, when in fact it is one of the most significant and well-supported propositions in theoretical cosmology. Time, in general relativity, is not a universal backdrop. It is a component of space-time, a dimension, yes, but one that is woven together with the three spatial dimensions into a single geometric structure. What we experience as the flow of time, the sense of events having a definite order, of causes preceding effects, of the past being fixed and the future being open, all of this emerges from the geometric structure of space-time. More specifically, it emerges from the causal structure of space-time, from the fact that, in relativity, light cones define which events can influence which other events. An event in your past can influence you. An event outside your past, light cone cannot. This causal structure is what gives time its directionality, its asymmetry between past and future. But this causal structure depends on space-time having a well-defined geometry. It depends on light cones being definite objects, on the metric of space-time being a smooth, well-defined function from point to point. At the Planck epoch, when space-time geometry is not smooth, when space-time is quantum foam, fluctuating and uncertain, the causal structure breaks down. Light cones are not well-defined. The question of which events can influence which other events does not have a definite answer. And if causal structure breaks down, temporal ordering breaks down. The notion that event A happened before event B, which seems so fundamental, so obviously true, so built into the very structure of experience, may not apply in the Planck regime. Events may not have a definite temporal order. The concept of one thing happening before another may be a large-scale, emergent approximation, one that works perfectly at the scales of everyday experience, but dissolves at the Planck scale. just as smooth ocean surfaces dissolve at the molecular scale. This is the foundation for a remarkable idea proposed by James Hartle and Stephen Hawking in 1983. Their no-boundary proposal describes the universe using a mathematical framework, the path integral formulation of quantum cosmology, in which the universe does not have a boundary in time. Instead of having a definite starting moment, a t equals 0 from which time stretches forward, the universe has a geometry in which the time dimension smoothly transitions into a spatial dimension near the origin. To borrow Hawking's own analogy, ask where the South Pole is on a globe. It is a well-defined point on the globe's surface. But ask what is south of the South Pole. There is nothing south of the South Pole. The question is not wrong because there is some mysterious answer we cannot access. It is wrong because the concept of south loses its meaning at the South Pole. The South Pole is not a boundary where the globe ends and something else begins. It is simply the point where the notion of south runs out. The Hartle-Hawking proposal suggests that the origin of the universe is analogous. The question, what happened before the Big Bang, is not a question with a hidden answer we cannot access. It is a question whose framing becomes undefined at the Planck Epoch, where before loses its meaning in the same way that south of the South Pole loses its meaning. The universe does not have a temporal edge with something on the other side of it. It has a geometric origin, a smooth beginning in which the time direction gradually emerges from what is initially a purely spatial geometry. Time, in this picture, is not fundamental. It is an emergent property of the universe's geometry, one that appears as you move away from the origin, but that does not exist in its usual sense at the origin itself. This is philosophically staggering. We are so accustomed to thinking of time as the most fundamental structure of reality, as the container within which everything happens, as the dimension along which causes lead to effects and effects become causes, that the idea of time being emergent, of time literally not existing in the early universe, is almost impossible to sit with. But the physics is serious, the mathematics is serious, and the implication that asking what happened before the Big Bang is asking about a direction that did not exist is one of the more honest answers modern cosmology has to offer to one of humanity's oldest questions. It is not satisfying in the way a narrative answer is satisfying. It does not give us a story of what came before. It tells us, with mathematical precision, that the story genre of before and after does not apply to this particular question. The universe, at its origin, may be the kind of thing for which we have not yet developed the right conceptual language. And this is perhaps the most important thing to take from this first act of our exploration. The Planck Epoch is the wall we cannot see past, not merely because it is technically inaccessible, not merely because our instruments cannot reach it, but because the very conceptual framework we use to describe physical events, the framework of things happening in space and time, of causes and effects, of before and after, may not apply there. The wall is not hiding a room. The wall may be the place where rooms cease to exist, where space, time, causality, geometry, the furniture of physical reality as we know it, have not yet appeared. We exist on the far side of a transition from something we have no description for to the universe we inhabit. And the question of what that something was, of what lies beyond the wall, or whether beyond even applies, is the deepest question in physics. What we know is this: every theory we have, every observation we have ever made, every piece of the physical universe we have ever touched or measured or described lives on this side of the wall. On the other side, that is where we are going next. And I promise you, it is stranger than you have imagined. Part 5. When all forces were one thing. On this side of the Planck wall, physics begins to work again, gradually, tentatively, but recognizably. The universe expands, it cools, and as it cools, something remarkable happens. The single unified interaction that governed the Planck epoch begins to fracture. Forces that were indistinguishable from one another at extreme energies begin to separate, like ice crystals forming in cooling water, each one taking on a distinct identity. What we now recognize as four separate forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were, in the first instance after the Planck epoch, something closer to one thing. And understanding this unification is not just a footnote to the Planck epoch story. It is the first chapter of the story of everything that came after, including you. At the temperatures corresponding to the Planck epoch, roughly 10 to the 32 Kelvin, a number so large it is essentially meaningless as a temperature in any ordinary sense, every particle in the universe had energies exceeding what physicists call the Planck energy, about 1.2 times 10 to the 19th giga-electron volts. For comparison, the most powerful particle accelerator humans have ever built, the Large Hadron Collider at CERN, achieves collision energies of about 14 tera-electron volts, which is 14 times 10 to the third giga-electron volts. The Planck energy is roughly 10 to the 15th times larger than what the LHC can produce. At those energies, the mathematical formalisms that describe the strong, weak, and electromagnetic forces as separate interactions are expected to merge into a single description. Gravity, which is already a geometric theory rather than a particle-mediated force in general relativity, is thought to join this unification at the Planck scale. This idea of force unification is not purely speculative, it has an observational track record. The electromagnetic and weak nuclear forces, which seem like completely different things at ordinary energies, were shown to be manifestations of a single electro-weak interaction in the 1970s through the work of Sheldon Glashow, Abdus Salam, and Steven Weinberg. This unification was confirmed experimentally with the discovery of the W and Z bosons at CERN in 1983. The forces really did unify. The universe really does work that way. At higher energies, apparently different forces reveal themselves as aspects of a deeper symmetry. The question is how far this goes. Does the strong force unify with the electro-weak at higher energies still? Most theoretical frameworks suggest it does, at energies around 10 to the 16th giga-electron volts, the so-called grand unification scale. And does gravity join the party at the Planck scale? Almost certainly yes, though we have no confirmed theory of how. This matters to our central story because it means that what we experience as distinct forces, the force that holds atomic nuclei together, the force that governs radioactive decay, the force that drives chemistry and electromagnetism, and the force that curves space-time and holds galaxies together, are all, in a deep sense, different aspects of a single underlying interaction that was unified in the Planck epoch. The diversity of physical law as we experience it, the rich complexity of chemistry, the behavior of light, the structure of matter, the architecture of the cosmos, all of that diversity is the result of a symmetry-breaking process that began as the universe cooled from the Planck epoch. The four forces are not four different things. They are four frozen fragments of one thing, shattered by the cooling of the universe from a temperature that no physics we possess can yet describe. And that shattering, that sequence of symmetry-breaking events that differentiated one unified interaction into the four forces we know, traces its origin back to the conditions in the Planck epoch. The wall we cannot see past is not just a wall hiding a moment. It is a wall hiding the unified state from which everything recognizable about the universe emerged. Part 6. The quantum foam reality nobody can visualize. If there is a single image that captures what physics believes about the Planck epoch more vividly than any other, it is Wheeler's quantum foam. And the reason it is so useful is not because it is easy to visualize, but precisely because it is not. The attempt to visualize it, To genuinely try to hold the image in your mind is itself a demonstration of the failure of classical intuition. And that failure is the point. We have already introduced the basic idea. At the Planck scale, space-time is not smooth but turbulent, not fixed but fluctuating, not a background but a dynamic quantum object. Let us now go deeper into what this actually means, because the implications are extraordinary. In ordinary quantum mechanics, the vacuum, empty space, is not actually empty. It is a seething sea of quantum fluctuations. Virtual particles and antiparticles constantly appear and annihilate. Fields fluctuate around their average values. The Heisenberg uncertainty principle, applied to field strengths rather than particle positions, guarantees that no field can be exactly zero. The vacuum has energy. It has structure. It is not nothing. This is not just theoretical. The Casimir effect, a measurable attractive force between two uncharged metal plates placed very close together in a vacuum, is a direct consequence of vacuum energy. The vacuum is demonstrably not empty. Now apply this idea, quantum fluctuations, in a vacuum, not to matter fields or electromagnetic fields, but to the gravitational field, to space-time itself. In quantum mechanics, every field fluctuates. If gravity is ultimately a quantum field, then the gravitational field fluctuates too, and the gravitational field is not just a force field existing in space. In general relativity, the gravitational field is space-time. The metric of space-time, the mathematical object that defines distances, angles, and causal relationships, is the gravitational field. So quantum fluctuations in the gravitational field are quantum fluctuations in the metric of space-time. They are fluctuations in distances, fluctuations in angles, fluctuations in whether two points are close or far, connected or separated. At ordinary scales, these fluctuations are vanishingly small, so small that space-time appears perfectly smooth at all scales accessible to any conceivable instrument. But at the Planck scale, the fluctuations become of order 1, comparable to the quantity being measured. Space-time geometry at the Planck scale is not slightly uncertain. It is completely uncertain. The metric fluctuates by amounts comparable to itself. There is no smooth background geometry. There is just the foam. Wheeler's quantum foam takes this further. In quantum mechanics, all possible configurations of a system contribute to its quantum state. This is the essence of the path integral formulation developed by Richard Feynman. For a particle moving from point A to point B, all possible trajectories contribute, not just the classical straight-line path. Similarly, for space-time, all possible geometries contribute to the quantum state of space-time. At ordinary scales, the contributions of exotic geometries, geometries with holes, with wormholes, with multiple connected components, are exponentially suppressed. The smooth, classical geometry dominates overwhelmingly. But at the Planck scale, where geometry itself is uncertain to order 1, this suppression disappears. All geometries contribute, geometries with wormholes, geometries with handles, geometries where space has a complicated, multiply-connected topology, geometries where the dimensionality itself is uncertain. All of these are part of the quantum superposition that constitutes the vacuum at the Planck scale. This means that at the Planck scale, the topology of space, the global structure of how regions are connected, is not fixed. In everyday experience and in classical physics, topology is permanent. You cannot smoothly deform a sphere into a torus. You have to tear a hole in it. Topology does not change under smooth deformations. But quantum mechanically, topological changes are possible through quantum tunneling. And at the Planck scale, these topological fluctuations are not rare events. They are the normal state of affairs. Space at the Planck scale is not a smooth surface. It is a structure in which wormholes are constantly appearing and disappearing, where the number of holes in space is not definite but is in quantum superposition where the connectivity of space fluctuates from moment to moment, or rather, where the concept of moment to moment itself is part of the geometry being fluctuated over. Stable distances do not exist at the Planck scale. The distance between 2 points, something so fundamental that geometry begins with it, is not definite. It fluctuates. The concept of a location, the idea that a point in space can be uniquely identified, loses meaning when the geometry itself is uncertain. You cannot say that something is at this place at this time, because this place and this time are themselves quantum uncertain objects. The furniture of classical physics, the background space and time against which everything else is described, is itself the thing that is undetermined. Physics cannot proceed without a background. Without a fixed stage on which events occur, the entire apparatus of field theory, of particle physics, of quantum mechanics as we understand it, cannot be applied. This is why the Planck Epoch is not just a hard problem. It is a problem that requires a complete reconceptualization of what physics is. The wall is not hiding a room with ordinary furniture. The wall is the boundary between the universe where physics as we know it operates, and a regime where the very presuppositions of physics are absent. Here is the vacuum, then, as the most violent entity in the universe, not in the colloquial sense of violence, but in the most literal physical sense. The vacuum at the Planck scale is not quiet. It is not still. It is a raging, topologically chaotic, geometrically undefined quantum superposition of all possible space-time structures, constantly fluctuating, with no stable geometry, no definite distances, no fixed topology, no causal structure. It is the opposite of nothing. It is everything at once, unresolved, superimposed, without a definite face. And our universe, smooth, expanding, causally ordered, hosting galaxies and stars and planets and you, emerged from that foam. The smoothness we see when we look at the cosmic microwave background, the remarkable uniformity of the universe on large scales, the fact that space has 3 dimensions and a single causal direction we call time, all of this is what you get when the quantum foam resolves. When one configuration of spacetime is selected out of the superposition by whatever process governs the transition from Planck Epoch to classical universe. The wall we cannot see past is the boundary between the foam and the world we know, and we have no description of how that transition happened. Part 7. The 4 competing theories of the wall. In the absence of experimental data from the Planck scale, and we will address why that absence may be permanent shortly, theoretical physicists have not stood still. They have constructed ambitious, mathematically sophisticated frameworks that attempt to describe what physics looks like in the regime where quantum mechanics and general relativity both become essential. There are currently 4 major candidates for a theory of quantum gravity, each approaching the wall from a different direction, each with distinct mathematical architecture and distinct physical predictions, and none of them confirmed by experiment. This is not a minor embarrassment for physics. This is the central, unsolved problem in fundamental physics, arguably in all of science. The fact that 4 serious, internally consistent frameworks exist without any ability to distinguish between them experimentally tells you something important about where we are in the history of understanding. We are in the pre-Newtonian position, intellectually speaking. We have the data, the existence of the Planck wall, the properties of black holes, the behavior of quantum fields in curved spacetime, but we do not yet have the framework that unifies them. String theory is the most famous of these candidates, and also the most ambitious. In string theory, the fundamental objects of nature are not zero-dimensional point particles, but one-dimensional strings, loops, or line segments whose different modes of vibration correspond to different particles. The different vibrational patterns of a string give rise to electrons, quarks, photons, and, crucially, the graviton, the hypothetical quantum of the gravitational field. String theory automatically includes gravity in its quantum description. It was discovered in the 1980s that any consistent quantum string theory requires not 4 dimensions but 10 dimensions, 9 spatial dimensions, and 1 time dimension, or in some formulations, 11 dimension. The extra dimensions beyond our familiar 3 spatial dimensions are currently compactified, curled up at scales far below what we can probe, but their geometry determines the specific form that the laws of physics take in our observable world. String theory is not one theory, but a landscape of theories, each corresponding to a different compactification geometry, and the number of consistent compactifications is estimated to be around 10 to the 500. This embarrassment of theoretical riches, the inability to select the compactification that corresponds to our universe without additional input, is one of the major criticisms of string theory as a predictive framework. Loop quantum gravity takes a completely different approach. Rather than replacing point particles with extended objects, loop quantum gravity applies the techniques of quantum mechanics directly to Einstein's general relativity without introducing any new fundamental objects. The result is a theory in which space-time itself is quantized, not infinitely divisible, but composed of discrete quantum elements. Space in loop quantum gravity is described by a network called a spin network, a graph whose nodes and links carry discrete quantum numbers representing areas and volumes. The areas of surfaces and the volumes of regions are not continuous quantities, but take discrete values, multiples of the Planck area and Planck volume. Time evolution in loop quantum gravity involves transitions between different spin network states, called spin foams, and the smooth, continuous spacetime of general relativity emerges from these discrete transitions at large scales, much as a smooth liquid emerges from the discrete interactions of molecules. In loop quantum gravity, the Planck length is a genuine minimum length. Space is not infinitely divisible. The wall at the Planck scale is, in this framework, the scale at which space reveals its discrete, granular structure. Causal dynamical triangulations is a approach that constructs spacetime by gluing together elementary simplices, the higher dimensional analogues of triangles, in a way that respects causality. The path integral over all possible spacetime geometries is approximated by a sum over all possible ways of assembling these building blocks, with the constraint that the resulting spacetimes have a well-defined causal structure. Computer simulations of this approach have produced encouraging results. The emergent geometry at large scales looks like the 4-dimensional de Sitter spacetime that describes our expanding universe. This is not a trivial result. Many naive approaches to quantum gravity produce spacetimes with wrong dimensionality or pathological properties. The fact that causal dynamical triangulations produces something like a realistic, large-scale geometry from discrete, causally constrained building blocks is a significant hint that this approach may be on the right track. Asymptotic safety is perhaps the most conservative of the 4 approaches. It proposes that gravity is not fundamentally different from the other forces and can be quantized using standard quantum field theory techniques, with the crucial addition that the theory has a fixed point in its renormalization group flow, a point at which the coupling constants of the theory stop changing as you go to higher energies, making the theory well-defined and finite at all scales. In this framework, the Planck scale is not a breakdown but a transition to a regime where gravity behaves in a qualitatively different but still well-defined way. There is no minimum length. Space does not become discrete. The theory simply flows to a different regime of coupling constants at high energies. What is striking about these 4 approaches is how differently they interpret the Planck wall. For string theory, the wall is the scale of string size, a minimum length below which the point particle description is replaced by extended objects. For loop quantum gravity, the wall is the granularity scale, the scale of the discrete quantum units of spacetime. For causal dynamical triangulations, the wall is the scale of the fundamental building blocks from which smooth geometry emerges. For asymptotic safety, the wall is not really a wall at all. It is a smooth transition to a well-defined but qualitatively different gravitational regime. None of these approaches agree on what the wall is, what it is made of, or what lies on the other side. This is not a situation where physicists are working out the details of an agreed framework. This is a genuine, deep-seated, theoretical uncertainty about the nature of reality at the smallest scales. And without experiment to adjudicate between them, it may remain unresolved for decades or longer. Part 8. Why experiments cannot touch it ever. There is a moment in every discussion of the Planck scale when the conversation shifts from the merely difficult to the potentially permanently impossible, and it is worth spending time on this because it changes the nature of what physics is trying to do in this regime. Science, in its most basic form, is the process of making predictions and testing them against observation. Theory and experiment are in constant dialogue. New theories make new predictions. Experiments test those predictions. Results either confirm or falsify the theory, and the field moves forward. This dialogue is the engine of scientific progress. The history of physics is the history of this dialogue, and at the Planck scale, that dialogue may be permanently severed. Consider the energy requirements. The Large Hadron Collider accelerates protons to energies of roughly 6.5 tera-electron volts per proton, producing collisions at around 14 tera-electron volts. This is an engineering achievement of extraordinary magnitude, a ring of superconducting magnets 27 kilometers in circumference, maintained at temperatures colder than outer space, consuming about as much electricity as a small city. It is the most powerful particle accelerator ever built, and the Planck energy is roughly 10 to the 15th times higher than the LHC's collision energy. To reach the Planck energy directly, using the same technology but scaling up, you would need an accelerator roughly 10 to the 15 times the size of the LHC. The LHC is 27 kilometers in circumference. Scale that up by 10 to the 15, and you get an accelerator whose circumference is roughly 2.7 times 10 to the 17 kilometers, about 28,000 light-years, bigger than the Milky Way galaxy. The Milky Way is roughly 100,000 light-years across, so the accelerator you would need to directly probe the Planck scale is comparable in size to a significant fraction of our galaxy. This is not an engineering problem in the ordinary sense. It is not the kind of thing where better materials or more efficient superconductors will get you there. The energy requirement is so many orders of magnitude beyond anything conceivable that direct experimental probing of the Planck scale is, for all practical purposes, impossible. And this is within our current theoretical framework. Even with some radically new acceleration mechanism, something we cannot currently imagine, the sheer energy required to resolve structure at the Planck length puts it beyond any foreseeable technology. Cosmic rays, which are high-energy particles that reach Earth naturally from astrophysical sources, achieve energies up to around 10 to the 21 electron volts, still about 10 to the 17 times below the Planck energy. The most energetic natural phenomena in the observable universe do not come close to the Planck scale. There are indirect approaches, ways of looking for quantum gravity effects without directly probing the Planck scale. Gamma-ray bursts from distant sources may show subtle energy-dependent differences in the speed of photons if spacetime has a granular structure at the Planck scale. The polarization of the cosmic microwave background may preserve imprints of primordial quantum gravity effects from the inflationary epoch. The spectrum of gravitational waves from the very early universe, if detectable, might encode information about conditions close to the Planck epoch. These approaches are being pursued seriously, but they probe Planck-scale physics only through its macroscopic consequences, faint, indirect signals filtered through billions of years of cosmic evolution. They test the downstream effects of whatever happened in the Planck Epoch, not the Planck Epoch itself. And distinguishing the quantum gravity signal from other physical effects in these observations is extraordinarily difficult. What does it mean for physics that its most fundamental questions may be permanently inaccessible to experiment? This is a question that the physics community is genuinely divided on. Some argue that a physical theory that cannot in principle be tested is not really a physical theory at all. It is mathematics, or philosophy, or educated speculation, but not science in the traditional sense. This was one of the major criticisms leveled at string theory during the early 2000s, that it had generated an enormous body of mathematical machinery without producing a single, clear, testable, distinctive prediction that could confirm or falsify it. Others argue that this is a limitation of our current experimental technology, not a fundamental barrier, that indirect tests or future technologies we cannot currently imagine may eventually provide constraints on quantum gravity theories strong enough to meaningfully distinguish between them. And others argue that the beauty and mathematical consistency of a theory, its ability to resolve known problems and produce a coherent picture, are themselves evidence that should be weighed even without direct experimental confirmation. This is not a purely academic debate. It goes to the heart of what science is. The Planck scale forces us to confront the possibility that the universe contains levels of structure that are not, even in principle, accessible to empirical investigation. The wall we cannot see past may not just be a wall we have not yet found the tools to scale. It may be a wall that the laws of physics themselves have made permanently opaque. And if that is true, then the deepest questions about the origin and nature of the universe, questions about what happened at the Planck Epoch, about whether the universe had a genuine first moment, about what lies beyond the singularity, may be questions that can never be answered by experiment. They may be questions where we have to proceed by mathematical consistency, theoretical elegance, and internal coherence alone, where physics shades into something that looks uncomfortably like metaphysics. That is a confrontation with the limits of knowledge that the physical sciences have not faced before in quite this form, and the Planck wall is where we face it. Part 9. The universe that shouldn't be this smooth. Here is something that sounds like it should be unremarkable, but is, upon reflection, one of the most extraordinary facts in all of observational science. When we look at the cosmic microwave background, the oldest light in the universe, the relic radiation from about 380,000 years after the Big Bang, it is almost perfectly uniform. The temperature of this radiation, measured in any direction you look, is about 2.7 Kelvin, about 2.7 degrees above absolute zero. And across the entire sky, in every direction, this temperature varies by only about 1 part in 100,000. The universe, at 380,000 years old, was almost perfectly smooth, homogeneous, isotropic, the same everywhere. This sounds like it should be reassuring. A smooth, uniform universe is a simple universe, a tidy universe, the kind of universe a physicist might hope for at the start of things. But think about it more carefully, and the reassurance dissolves into something deeply unsettling. The cosmic microwave background was emitted when the universe was roughly 42 million light-years across in terms of co-moving distance. 2 points on opposite sides of the observable universe at that time were separated by roughly 42 million light-years. And light, in the roughly 380,000 years that had elapsed since the Big Bang, could only have travelled about 380,000 light-years, about 1% of the separation between those points. Think about what this means. 2 regions of the early universe, sitting at precisely the same temperature, had no way to have communicated with each other, no way to have exchanged energy or information, no way to have reached any kind of equilibrium through any known physical process, by the time we observe them to be in thermal equilibrium. They are at the same temperature without ever having been in causal contact. Imagine two people on opposite sides of a planet who have never met, never sent a letter, never communicated in any form, and yet who have, independently, arrived at the exact same answer to an extraordinarily precise question. That would be astonishing. This is more astonishing still, because it is not two people but billions of causally disconnected patches of the early universe, all agreeing on a temperature to within 1 part in 100,000. In the language of physics, this is called the horizon problem, and it is a deep, genuine puzzle, not a puzzle of the kind that awaits only better data, but a puzzle of the kind that points toward a gap in our fundamental understanding of how the universe began. Why is this a puzzle that connects back to the Planck Epoch? Because the smooth initial conditions of the universe, the uniformity of the cosmic microwave background, the near-perfect homogeneity of the early universe are not explained by anything that happened after the Planck Epoch. They are initial conditions. They were set at or near the Planck Epoch, that first sliver of time, the first 10 to the negative 43 seconds of cosmic history, when the universe was so hot and dense that the known laws of physics simply ceased to apply. Whatever process produced the universe from the Planck wall produced it with these extraordinarily precise initial conditions already in place. The smoothness of the universe that we observe today is not something the universe evolved toward through physical processes that we understand and can model. It is something the universe started with, and where it started from is the Planck Epoch, the wall we cannot see past. That wall is not just hiding some abstract quantum gravitational physics that would only matter to theorists. It is hiding the origin of every specific feature of the universe we observe. The temperature of the cosmic microwave background, the spatial flatness of the universe, which is so precise that after nearly 14 billion years of expansion, the geometry of space is still indistinguishable from perfectly flat. The particular spectrum of density fluctuations from which galaxies and galaxy clusters and the vast filamentary web of large-scale structure eventually formed. All of these trace back to initial conditions that were set in the Planck Epoch. The standard solution to the horizon problem is inflation, the proposal introduced by Alan Guth in 1980 that the very early universe underwent a period of extremely rapid, accelerating expansion, driven by the energy of a quantum field caught in a metastable state, like a ball sitting at the top of a hill before rolling down into a lower energy valley. During inflation, the scale factor of the universe increased by a factor of at least 10 to the 26 in an incredibly brief time, possibly as short as 10 to the negative 32 seconds. To appreciate the violence of this expansion, consider that it is the equivalent of taking something the size of a proton and expanding it to the size of the observable universe, not gradually, but in less time than it takes light to cross a single atomic nucleus. This explosive expansion took a tiny region of the universe, small enough to be in thermal equilibrium, and stretched it to encompass everything we can currently observe. The uniformity of the cosmic microwave background in this picture is the uniformity of that original tiny region, blown up to cosmic scales the way a nearly uniform surface becomes clearly smooth when you zoom in close enough. The horizon problem disappears because the regions we observe to be in thermal equilibrium were, before inflation, in genuine causal contact. They had time to exchange energy and reach the same temperature. Inflation solved the problem not by explaining the equilibrium, but by making the observable universe far smaller before inflation than a naive calculation would suggest, small enough that equilibrium was achievable through ordinary thermodynamic processes. Inflation also produces another crucial prediction, one that has elevated it from a clever solution to a problem into something approaching a scientific framework with genuine empirical content. Quantum fluctuations during inflation, tiny, unavoidable variations in the energy of the inflaton field, governed by the same quantum mechanics that determines the behavior of electrons in atoms, gets stretched by the inflationary expansion to macroscopic scales. These quantum fluctuations, imprinted on the fabric of the early universe, become the seeds of density variations that later grow, under gravity, into the galaxies and filaments and voids that make up the large-scale structure of the cosmos. The specific statistical signature of these fluctuations, their nearly scale-invariant spectrum, their particular pattern of correlations, is a prediction that inflation makes and that can be tested. These predictions have been tested against observations of the cosmic microwave background with remarkable precision. The spectrum of temperature fluctuations in the CMB, their statistical properties, their dependence on angular scale, matches the predictions of inflation with accuracy that is genuinely impressive, the kind of quantitative agreement that, in other branches of physics, we would regard as strong evidence that a theory is on the right track. Inflation is, in this observational sense, one of the most successful theoretical frameworks in modern cosmology. It is taken seriously not because it is elegant, though it is, and not because it solves a genuine puzzle, though it does, but because it makes specific, falsifiable predictions, and those predictions have held up. But here is the crucial caveat, and here is where the Planck wall re-enters the picture with full force and refuses to be dismissed. Inflation explains the smoothness of the universe by positing a rapid expansion that took place after the Planck Epoch, somewhere around 10 to the negative 35 seconds, a time when the universe had already cooled below the Planck energy and quantum gravity effects were no longer dominant. Inflation operates, in other words, in a regime where physics as we know it is at least partially applicable. But inflation does not explain its own initial conditions. For inflation to begin, the universe had to start in a particular state with the inflaton field in its metastable, high-energy configuration, poised to drive the exponential expansion, and with space-time already smooth enough, already calm enough, that inflation could proceed in a coherent and effective way rather than being disrupted by wild quantum gravitational fluctuations. Where did those initial conditions come from? The honest answer, the answer that anyone reasoning carefully about the chain of causation must eventually arrive at, is from the Planck Epoch. Inflation is a mechanism for processing initial conditions, a kind of cosmic amplifier and smoother that takes the conditions immediately after the Planck Epoch and produces, as output, the smooth, flat, fluctuation-imprinted universe that we observe. But it is not a mechanism for generating those initial conditions from nothing, or for explaining why the universe began in a state suitable for inflation rather than in some other, less hospitable configuration. The starting state of inflation is itself a product of the Planck Epoch, and therefore inaccessible to our current physics. Inflation pushes the mystery back, but it does not dissolve it. The mystery waits, unchanged, behind the Planck wall. Roger Penrose has made this point in a particularly striking and disquieting way. The initial state of the universe, the state from which inflation began, the state that eventually produced the smooth, structured, life-permitting cosmos we inhabit, was a state of extraordinarily low entropy. Not low entropy in a casual or approximate sense, but low entropy in a way that, by Penrose's calculation, required the universe to be in a configuration so improbable, so finely tuned among all possible configurations it might have occupied, that the probability of it occurring by chance would be 1 in 10 to the 10 to the 123. Let that number settle for a moment, because no analogy will do it justice. It is a number so large that it is not merely larger than the number of atoms in the observable universe. It is vastly larger than the number of atoms in the observable universe raised to the power of the number of atoms in the observable universe, raised again to any power you might choose to write down. The universe began in an almost incomprehensibly special state, not a state that any reasonable probabilistic argument would lead you to expect. not a state that inflation produces, since inflation itself requires this state as a precondition, a state that was not produced by any physical process we can describe or model, a state that was, in the most literal sense, handed to the universe as a starting gift by whatever dynamics governed the Planck epoch. The smoothness and structure of the universe we observe are therefore not just interesting facts about cosmology. They are downstream consequences of an initial condition of extraordinary, almost incomprehensible specificity, a condition that traces back, without detour or escape, to the wall we cannot see past. Every galaxy that formed, every star that ignited, every planet that coalesced from the debris of those stars, every chemical process that led to life on at least one of those planets, is a consequence of a pattern of density fluctuations that traces back to quantum noise during inflation, which traces back to the state of the inflaton field at the beginning of inflation, which traces back to conditions set in the Planck epoch, which traces back to physics we do not have. Understanding the Planck epoch is therefore not merely an academic exercise in quantum gravity. It is not just about understanding the first instant of the universe in some narrow, technical sense. It is about understanding why the universe is the way it is at all, why it has galaxies rather than a featureless maximum entropy soup, why it has the geometry it has, why it has the large-scale structure it has, why it has, in the end, the conditions necessary for anything interesting to exist within it. The Planck wall is not merely the beginning of time, it is the origin of every specific thing that time has since produced. And we cannot see past it. Part 10. Competing explanations for what the wall is. We have now seen what the Planck wall is, the scale at which general relativity and quantum mechanics simultaneously break down, the scale at which space-time ceases to be smooth, the scale at which the initial conditions of the observable universe were set. The next question is what the wall means, what kind of thing it is. Is it a physical boundary, an edge of existence beyond which there is genuinely nothing? Is it an artifact of our own ignorance, a place where our maps run out but the territory continues? Or is it something stranger, still a threshold, a transition between modes of being so different from one another that the language we use for one may be entirely inapplicable to the other? Physics, at present, offers three distinct and mutually exclusive interpretations of the Planck wall, each with its own implications for the nature of reality, for the structure of space and time at their most fundamental level, and for the question of whether the universe has a genuine beginning in any meaningful sense of that word. The first interpretation is that the wall is real. Not real in the sense of being an obstacle that exists within space-time, but real in the deeper sense of representing a genuine minimum structure of space-time itself, a physical discreteness at the Planck scale below which there is simply nothing, no smaller distances, no earlier times, no further divisibility. Space, in this picture, is not infinitely divisible, not a smooth continuum that can be sliced ever more finely without limit. It is, instead, granular, quantized, built from fundamental units below which the concept of smaller loses not just practical meaning but physical meaning. Time is not a continuous river flowing from the past toward the future at arbitrarily fine resolution. It is, instead, composed of discrete ticks, the Planck time, each about 5 × 10⁻⁴ seconds, below which the question of when simply has no answer, not because the answer is hidden or inaccessible, but because the question itself is malformed. This is essentially the picture that emerges from loop quantum gravity, one of the two leading candidates for a theory of quantum gravity developed over several decades by Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and their collaborators. In loop quantum gravity, space is not a smooth backdrop against which physical events take place. It is a physical entity in its own right, and like other physical entities in quantum mechanics, it is quantized. The geometry of space areas, volumes, the curvature of the fabric of the cosmos comes in discrete packets, the smallest of which are set by the Planck length. Below the Planck length, there is no geometry, there is no space. The Planck length is not the smallest thing we can measure. It is the smallest thing that exists. The consequences of this view are profound and, in some ways, vertiginous. Asking what happened at a time shorter than the Planck time, or at a distance smaller than the Planck length, is not like asking what is beyond the edge of a map that could, in principle, be extended. It is like asking how many electrons are in half an electron. The question is not wrong because the answer is difficult to calculate or experimentally inaccessible. It is wrong because the premise is false. There is no structure below the Planck scale. The wall is the bottom. The universe does not have an earlier history that we simply cannot see. It does not have a smaller structure that we simply cannot probe. There is no other side. The Planck wall, in this interpretation, is not a wall in the sense of a barrier behind which something lies hidden. It is a wall in the sense of a floor, the place where downward motion simply ends, not because something stops you, but because down has ceased to exist. The second interpretation is that the wall is ignorance, not ignorance in a pejorative sense, not a failure of intelligence or effort, but ignorance in the precise epistemological sense, a reflection not of a genuine minimum structure of space-time, but of the incompleteness of our theories. In this view, space-time may well be continuous and infinitely divisible, and the Planck scale is simply where our current theoretical frameworks break down, because they are approximations to something deeper and more accurate that we do not yet possess. The wall marks not the edge of reality, but the edge of our current map. Beyond it, reality continues, describable in principle by a theory we have not yet found, governed by physics we have not yet uncovered, structured in ways we cannot yet articulate. The historical analogy here is instructive and worth taking seriously. Newtonian mechanics was, for 2 centuries, the most successful physical theory ever constructed. It described the motion of planets, the fall of objects, the behavior of fluids, the propagation of waves, all with extraordinary precision. And then, at high velocities approaching the speed of light, it broke down. It gave wrong answers. It produced inconsistencies. The breakdown of Newtonian mechanics at high velocities was not a sign that space and time had a fundamental limit at those velocities, that the universe became granular or ill-defined as objects moved faster. It was a sign that Newtonian mechanics was an approximation to a deeper theory, special relativity, that happened to be indistinguishable from Newtonian mechanics at low velocities but diverged from it sharply at high ones. The breakdown was a feature of the map, not the territory. Relativity did not find a minimum velocity below which physics stopped. It found a more accurate description of physics at all velocities. Perhaps the breakdown of general relativity and quantum mechanics at the Planck scale is the same kind of signal. Perhaps it tells us not that space-time has a minimum structure, but that our theories are approximations to something deeper, a theory of quantum gravity that reduces to both general relativity and quantum mechanics in their respective domains of applicability, just as relativity reduces to Newtonian mechanics at low velocities. In this view, the singularity at the Planck epoch is not a genuine physical infinity, not a real breakdown of reality, but an artifact of the approximations built into our current theories. When the correct theory is found, it will describe physics through and beyond the Planck scale without encountering any wall at all. The singularity will dissolve, revealed as a mathematical pathology of an incomplete framework rather than a feature of the world. This is the view suggested by approaches like asymptotic safety in quantum gravity, where the Planck scale is a transitional regime, a region where coupling constants flow to a fixed point and the theory remains well defined rather than a fundamental cutoff where physics ends. This interpretation carries its own distinctive implications. If the wall is ignorance, then the question of what happened before the Planck epoch is, in principle, answerable. it has a real answer. The universe at times earlier than 10 to the negative 43 seconds was in some definite physical state, governed by some definite physical laws, and what we need in order to know what that state was and what those laws were is not better experiments alone, but better theory. The obstacle is not ontological. It is not a feature of how the world is, but epistemological. It is a feature of how much we currently understand. This is, in a certain sense, the most optimistic of the three interpretations. It implies that the mystery of the Planck wall is, at least in principle, solvable. The universe has no genuine secrets at the Planck scale, only secrets from us at this moment in the history of inquiry. The third interpretation is that the wall is a phase transition, a genuine physical transition between different states or phases of the universe, analogous to the phase transitions between solid, liquid, and gas that govern the macroscopic behavior of matter. In this view, the Planck epoch is not a place where physics breaks down, and not merely the limit of our current knowledge, but a place where the universe transitions from one phase to another phases so different from each other that the concepts and structures we use to describe one may have no analogue, no translation, no equivalent in the other. The wall, in this interpretation, is not an edge and not a limit of knowledge. It is a doorway, a boundary between phases of the cosmos that differ from each other as profoundly as ice differs from steam, not just quantitatively in temperature or density, but qualitatively in structure, in symmetry, in the very organization of their constituents. What might these phases actually look like? This is where the interpretation becomes genuinely strange and genuinely interesting. Some approaches to quantum gravity suggest that the phase on the other side of the Planck wall might be one in which time and space are not separate entities, as they are in our phase, but are unified in a way that makes the distinction between them meaningless. In our current phase, time has a direction, the past is different from the future. Entropy increases, causes precede effects. In the earlier phase, this directionality might not exist. The universe might have had a geometry in which what we call time behaved more like what we call space, having extent, but no preferred direction, no arrow. Stephen Hawking's no boundary proposal gestures toward this idea, imagining that the early universe had a Euclidean geometry in which the time dimension was effectively a spatial dimension, and that the transition from that Euclidean geometry to the Lorentzian geometry of our current universe was the phase transition that defines the Planck wall. The number of large dimensions might have been different. The effective laws of physics, the symmetries, the fundamental constants, might all have emerged from this transition as properties specific to our phase, the way the macroscopic properties of ice, its crystalline structure, its rigidity, its optical properties, emerge from the phase transition that produces it from liquid water, without being fundamental features of water molecules themselves. This interpretation is related to ideas in causal dynamical triangulations, where smooth four-dimensional spacetime emerges as a macroscopic phase from a more fundamental combinatorial structure of discrete causal building blocks. In this framework, the smooth spacetime we inhabit is not fundamental. It is a collective, emergent phenomenon, like the smoothness of the surface of water emerging from the chaotic, discrete motion of individual molecules. At the Planck scale, the smooth surface breaks down and the discrete molecular structure is revealed, but the molecular structure is not nothing, and the breakdown of the smooth description does not mean that there is no further description to be had. It means the description changes character entirely. These three interpretations, minimum structure, ignorance, and phase transition, cannot currently be distinguished by experiment. This is not a temporary embarrassment awaiting better technology. It reflects the depth of our epistemic situation. All three are mathematically consistent, at least at the level we can currently work out. All three reproduce the known physics of general relativity and quantum mechanics at large scales, where those frameworks have been tested with extraordinary precision. All three make qualitatively different predictions about the nature of the universe at and beyond the Planck scale. Predictions about whether the universe has a genuine beginning, about whether time is fundamental or emergent, about whether the laws of physics we observe are inevitable features of reality or contingent properties of the particular phase we happen to inhabit, and we currently have no way to test any of those predictions. No particle accelerator we can build will reach Planck energies. No telescope we can construct will see through the Planck wall. No experiment we can design will tell us whether space-time is discrete or continuous, or neither. This is the deepest epistemic situation in physics, perhaps the deepest in all of science. Three pictures of what reality is at its most fundamental level, all consistent with everything we know, all making different claims about the nature of existence, and no foreseeable way to choose between them. The wall does not merely hide information from us in the way that a locked room hides its contents. It hides the answer to a prior and more unsettling question, the question of what kind of thing information is, what kind of thing space and time are, what kind of thing existence itself is, at the most fundamental level we can conceive of asking about. We do not know what is on the other side of the wall. We do not know with any certainty whether the phrase other side is even meaningful. And that uncertainty is not a gap in our knowledge waiting to be filled. It is, at present, the boundary of what the human mind has been able to make physical sense of at all. Part 11. The most radical idea, no first moment. Perhaps the most radical response to the problem of the Planck wall is to question the premise. The premise is that the Big Bang represents something like the beginning of the universe, that the Planck Epoch is close to, or identical with, the origin of everything, the moment before which there was no moment, the event before which there was no event, the first page of a book that had no cover. What if it is not? What if the universe has no first moment? Not in the sense that the first moment is hidden behind an impenetrable wall, not in the sense that it exists but cannot be accessed, but in the deeper and stranger sense that there was no first moment. That the universe, in some form, has always existed, that asking when it began is like asking where a circle starts, not a difficult question, but a confused one. This is not a fringe idea. It is not the province of philosophers, unwilling to accept the conclusions of physics, or of mystics projecting their intuitions onto the cosmos. Some of the most serious and mathematically sophisticated proposals in theoretical cosmology suggest exactly this, each of them approaching the question from a different direction, each of them with a different mechanism for dissolving the singularity, for replacing the apparent beginning of the universe with something that does not require a first moment, that does not demand that something came from nothing, that does not leave the initial conditions of the observable cosmos as a brute, inexplicable given. These proposals do not all agree with each other. They make different claims about the structure of time, the geometry of space, and the nature of what might lie on the other side of the Planck wall. But they share the conviction that the wall is not a terminus, and in their disagreements and their convergences, they sketch the outermost boundary of what cosmological imagination has so far been able to conceive. Loop quantum cosmology, the application of the discrete, quantized space-time framework of loop quantum gravity to the universe, considered as a whole, produces one of the most striking and conceptually clean of these alternatives. The starting point is the recognition that the Big Bang singularity, the infinite density, the infinite curvature, the point at which the classical equations of general relativity simply break down and return nonsensical values, is not necessarily a feature of physical reality. It may be a feature of the mathematical framework used to describe physical reality. Classical general relativity treats spacetime as a smooth, continuous manifold, infinitely divisible, structured at arbitrarily small scales. Loop quantum gravity denies this. In loop quantum gravity, space is quantized. It comes in discrete units. You cannot divide it below the Planck length because there is nothing below the Planck length. And when you apply this quantized description of spacetime to the problem of a collapsing or expanding universe, something remarkable happens. The singularity disappears. In the classical general relativistic description, a contracting universe collapses toward a singular point of infinite density. In the loop quantum cosmological description, something different occurs. As the universe contracts and reaches a size comparable to the Planck scale, the quantum geometry of space generates a repulsive effect, a pressure, arising not from any conventional form of matter or energy, but from the fundamental discreteness of space-time itself. This quantum repulsion is sufficient to halt the collapse before it reaches a singularity. The universe does not crunch to a point. It compresses to a minimum volume, a smallest possible size set by the Planck scale, and then bounces. The contraction becomes an expansion. What we call the Big Bang is, in this picture, not a beginning but a bounce, the moment of maximum compression in a universe that was previously contracting, the turning point after which expansion takes over. Our entire observable cosmos, with its 14 billion years of expansion and cooling and structure formation, is the post-bounce phase of a universe that existed in contracting form before the Big Bang. The Planck Epoch is not where time begins. It is where one phase of time gives way to another. The wall between our universe and what came before is real, in the sense that physics as we know it breaks down there, but it is a doorway, not a terminus, a seam in the fabric of time rather than its edge. This picture immediately raises questions. What was the pre-bounce universe like? Did it have structure, matter, galaxies, a history comparable to our own? Could any information about it have survived the bounce and be detectable in the properties of our universe? These questions are, at present, at the frontier of research in loop quantum cosmology, with some results suggesting that certain signatures of the pre-bounce phase might be imprinted on the cosmic microwave background at angular scales not yet fully probed by observation. The bounce, in other words, might not be entirely opaque. The wall might have cracks. Roger Penrose's conformal cyclic cosmology is a different and more radical proposal, one that arrives at a similar conclusion that the universe cycles, that there is no beginning, by an entirely different and deeply counterintuitive route. Penrose begins not with the beginning of the universe, but with its end. He asks what the ultimate fate of our cosmos will be, in the very long run, after all the stars have burned out and the galaxies have dispersed and the black holes have evaporated through Hawking radiation, one by one, over timescales so vast they make the current age of the universe look like the first microsecond of history. His answer is a universe consisting solely of photons and other massless particles, drifting through an immense, cold, nearly featureless expanse. No massive objects, no atoms, no molecules, no dust. In such a universe, Penrose argues, something crucial is lost: the ability to define scale. Mass is what gives objects the ability to measure distances and durations. Massive particles have Compton wavelengths, massive clocks can tick, massive rulers can measure. Remove mass from the universe entirely, and the distinction between large and small distances, between long and short time intervals, becomes physically meaningless. The universe becomes scale-free, and a scale-free universe is, in a precise mathematical sense, conformally equivalent to a new Big Bang. The cold, diffuse, massless end state of one universe is conformally rescaled, transformed by a mathematical operation that preserves angles and shapes, but not sizes, into the hot, dense, apparently singular initial state of the next. The end of one aeon is the beginning of another. Universes succeed each other in an infinite sequence. Our Big Bang was the conformally rescaled death of a previous cosmos. Our own distant future will be the birth of a cosmos we will never see. The Planck Epoch, in Penrose's picture, is not an origin. It is a transition between eons, the hinge between one chapter of an infinitely long story and the next. And the story has no first chapter. Alan Guth's eternal inflation goes further still, in a different direction, producing a picture that is in some ways more extravagant than either the bouncing universe or the cyclic cosmology. In the standard inflationary picture, the period of rapid exponential expansion that preceded and produced our observable cosmos occurred when a quantum field, the inflaton, was trapped in a metastable, high-energy state. Eventually, the field tunneled out of that state, inflation ended, and the energy of the inflaton field was converted into the hot plasma of particles that constitutes the conventional Big Bang. But inflation is a quantum process, and quantum processes are probabilistic and spatially variable. In some regions of the inflating universe, the field tunnels out and inflation ends, producing bubble universes like our own. In other regions, the exponential expansion continues, and quantum fluctuations keep the field in its high-energy state, driving further inflation. And crucially, inflation is so rapid, the expansion so extreme, that the regions where inflation continues grow faster than the regions where it ends can consume them. The inflating background is never depleted. New bubble universes constantly nucleate within it, each one expanding from its own local Big Bang, each one potentially harboring its own physical constants, its own laws of physics, its own version of the story of cosmic evolution. Our observable universe is one such bubble, one local region where inflation happened to end, embedded in an eternally inflating background that has no global beginning and will have no global end. It simply produces universes, endlessly, as a kind of cosmic inevitability. In this picture, the question of what happened before our Big Bang receives a concrete and remarkable answer. Before our Big Bang, there was the inflating bulk, the eternally expanding quantum field theoretic background from which our bubble nucleated. That background was not empty. It was a seething, quantum fluctuating medium driving exponential expansion, populated by other bubbles that had nucleated at other times and places, each one a universe in its own right, separated from all the others by the expanding, inflating bulk. Our Planck wall is local. It is the boundary of our bubble, not the boundary of all existence. On the other side of our wall is not nothing and not a previous contracting universe, but an eternal inflationary process that predates our Big Bang by an infinite amount of time and will postdate our cosmic future by an infinite amount of time as well. The universe, in this picture, is not large. It is, in the most literal sense, boundless. The Hartle-Hawking no-boundary proposal approaches the problem from yet another angle. Rather than positing a pre-existing universe that bounces, cycles, or inflates, Hartle and Hawking suggest that the question of what happened before the Big Bang is not a question that has an answer not because the answer is hidden, but because the question is grammatically correct but physically meaningless. Before the Big Bang, in their picture, time as we know it did not exist. The time dimension of the universe transitions, near the Planck epoch, from Lorentzian with a clear distinction between past and future, between time and space, to Euclidean, in which the time dimension becomes indistinguishable from a spatial dimension. In Euclidean geometry, there is no preferred direction, no earlier and later, no arrow. Asking what happened before the Big Bang in this framework is like asking what is south of the South Pole. There is no south of the South Pole. The question presupposes a structure, a direction, a before that does not exist at that location. The universe has no boundary in the Euclidean regime, and therefore no beginning in any conventional sense. It simply is, smoothly and boundarylessly, with the Lorentzian time dimension we experience emerging from the Euclidean geometry the way a phase emerges from a transition, not at a sharp edge, but through a smooth, geometric process that has no natural first moment. The ekpyrotic model offers yet another alternative geometry for the cosmos. In this framework, our universe is a three-dimensional surface, a brane embedded in a higher dimensional space. Another brane exists nearby, separated from ours by a tiny gap in the extra dimension. The Big Bang, in the ekpyrotic picture, was not the expansion from a singular point, but the collision between these two branes, a high-energy impact that produced the hot, dense plasma of the early universe. The singularity is replaced by a collision event, a perfectly finite, physically well-defined occurrence. And the branes, after colliding and bouncing apart, may eventually be drawn back together by the tension of the higher dimensional space and collide again, producing another Big Bang, another cycle, another universe constructed from the wreckage of the previous one. What is striking about this proliferation of alternatives, the bounce, the cyclic eons, the eternal inflation, the no-boundary geometry, the brane collision, is that they are not merely a list of creative possibilities. They share a common theme, a common conclusion that they arrive at by radically different routes. The Planck Epoch is not an origin but a transition, a bounce, a collision, a conformally rescaled end, a bubble nucleation, a place where time becomes space. In every one of these frameworks, the universe we observe is not the first thing that existed. It is a transformation of something earlier, something that passed through the Planck wall and emerged as the expanding, cooling, structure-forming cosmos we call home. The Big Bang is not the beginning of everything. It is the beginning of this configuration of everything. The wall we cannot see past is not the edge of the universe. It is the seam between one chapter of reality and whatever chapter came before, if before even applies. And we are only on one page of a document whose total length we cannot determine, in a language we are only beginning to learn, in a library whose existence we inferred from a single shaft of light falling through a single crack in a wall we cannot open. And we are only on one page. Part 12. Standing at the wall. Come back to the image we started with. 10 to the negative 43 seconds. Not a long time, not a short time, in the ordinary sense. A duration so far outside the range of human experience that the word duration barely applies. And yet it is a real number. It is a specific quantity derived from the constants of nature that defines a specific threshold in the history of the universe. And everything, absolutely everything in the observable universe, every particle, every force, every quantum of energy, every gravitational wave, every atom that has ever been part of a living thing, passed through this threshold. The universe did not begin here, in the sense that a story begins on its first page. It emerged here in the sense that a river emerges from a spring, from something earlier, or earlier adjacent, or definitionally prior, that we cannot see. There is a kind of vertigo that comes from thinking carefully about this. We speak about the history of the universe with great confidence. We can describe what happened at 1 second after the Big Bang, protons and neutrons in a plasma beginning to fuse into helium nuclei. We can describe what happened at 3 minutes, Big Bang, nucleosynthesis, the universe's first chemistry. We can describe what happened at 380,000 years, recombination, the release of the cosmic microwave background, the universe becoming transparent for the first time. We can describe the formation of the first stars, roughly 100 to 200 million years after the Big Bang, the first galaxies, the large-scale structure of the cosmos. We have a detailed, observationally grounded account of the universe from about 1 second onward. We have solid, though less directly observable, theoretical understanding back to about 10 to the negative 35 seconds during inflation. Before that, things become less certain. before 10 to the negative 43 seconds, the physics breaks. And everything we know, everything in that detailed, confident, observationally grounded account, depends on initial conditions that were set in the regime we cannot describe. Think about what it means that our two greatest physical theories both fail simultaneously at this threshold. General Relativity has described the bending of light around the sun to extraordinary precision, predicted the existence of gravitational waves a century before they were detected, and provided the mathematical framework for understanding black holes, neutron stars, and the expansion of the universe. Quantum mechanics has given us the transistor, the laser, the MRI scanner, and a description of the structure of matter that is accurate to more decimal places than almost any other measurement in science. These are not failed theories. These are the most successful, most tested, most verified frameworks in the history of human knowledge. And they are both, simultaneously, completely inadequate to describe the Planck Epoch. The most successful bodies of knowledge in human history fail together at this single threshold. What should this tell us? It should tell us that whatever is on the other side of the wall, whatever the Planck Epoch actually was, whatever governed the universe at that scale, is genuinely, qualitatively different from everything physics has so far described. It is not an extreme version of something we know. It is not hot quantum field theory pushed to higher energies. It is not curved space-time pushed to higher curvatures. It is something for which we do not yet have a description, something that requires new concepts, new mathematics, possibly a new understanding of what space and time and causality are at their most fundamental level. The failure of our two best theories at the same scale is not a coincidence. It is a signal. It is the universe telling us that we have reached the edge of what these frameworks can handle, that what lies beyond requires something fundamentally new. 100 years of physical theory, from quantum mechanics in the 1920s, through quantum field theory in the 40s and 50s, through the electroweak unification in the 70s, through the inflationary cosmology of the 80s, through the discovery of dark energy in the 90s, through the detection of gravitational waves and the imaging of black holes in the 2010s, all of it, every major advance of the last century, converges on a single scale, 10 to the negative 43 seconds, 1.6 times 10 to the negative 35 meters, the Planck Epoch. The more powerful our theories become, the more precisely they point to this threshold as the place where they themselves stop working. This is not a failure, it is an achievement. 100 years of increasingly precise science has succeeded in identifying the exact scale and nature of its own limit. That is remarkable. But it also means we are standing at the wall, and the wall is not getting closer. We are as close to it as empirical science can currently take us, perhaps as close as empirical science can ever take us. Let us be clear about what we know and what we do not know, because honesty requires this. We know that general relativity and quantum mechanics are incompatible at the Planck scale. We know, from indirect arguments, that space-time almost certainly loses its smooth classical structure at or near the Planck length. We know that the initial conditions of the observable universe, its smoothness, its flatness, its specific spectrum of density fluctuations, trace back to the Planck epoch. We know that several theoretical frameworks for quantum gravity exist, each with different pictures of what the Planck scale is like, and that none of them are experimentally confirmed. We know that direct experimental probing of the Planck scale is, for all practical purposes, not possible with any foreseeable technology. And we know that the question of whether the universe had a genuine first moment, or whether the Planck epoch is a transition from something earlier, remains genuinely open, with serious theoretical frameworks on multiple sides of the question. What we do not know is vastly larger. We do not know what theory correctly describes physics at the Planck scale. We do not know whether space-time is fundamentally discrete or continuous. We do not know whether the universe had a beginning or has always existed in some form. We do not know whether the singularity at the heart of the Big Bang represents a real physical feature of the universe or an artifact of our incomplete theories. We do not know whether there is a multiverse. We do not know whether time is fundamental or emergent. We do not know whether the laws of physics that operate in our universe are the only possible laws, or whether they are one selection from a vast space of possibilities. We do not know what quantum gravity is, and we do not know whether any of these questions are answerable, in principle, by empirical science, or whether they belong to a category of questions that can only be approached through mathematical consistency and theoretical coherence, divorced from experimental test. 3 possible answers to the central question, is the wall a doorway or an edge, remain viable. The first is that the wall is a limit of reality. Space-time is genuinely discrete at the Planck scale. There is a minimum length and a minimum time, and asking what happened before the Planck time is like asking what is smaller than the smallest thing. The question is not wrong, but the answer is a clean, definite nothing. The second is that the wall is a limit of knowledge. Our theories are incomplete. A deeper theory of quantum gravity will eventually describe the Planck Epoch and whatever lies beyond it, and the apparent impenetrability of the wall is a feature of our current ignorance rather than of the universe itself. And the third is that the wall is an interface between states of the cosmos. The Planck Epoch is a phase transition between a pre-Big Bang state, a collapsing previous universe, an inflating bulk, an aeon of massless particles, a brain collision, and the expanding universe we inhabit. And understanding that transition is the key to understanding not just where our universe came from, but what kind of thing a universe is. Physicists are currently divided, more or less equally, between these 3 possibilities. This is not a situation where there is a leading candidate and some outliers. These are genuine, serious, mathematically sophisticated positions held by some of the most brilliant theorists alive. And without experiment, without some indirect probe, some unexpected observation, some theoretical breakthrough that allows us to distinguish between them, the question may remain open for a very long time. Here is what that should feel like if you sit with it properly. You are made of atoms. Those atoms were forged in the cores of stars that lived and died before the sun was born. Those stars were made of hydrogen and helium, produced in the first 3 minutes after the Big Bang. That hydrogen and helium emerged from a hot, dense plasma that was itself the product of an inflating universe, that was itself the downstream consequence of initial conditions set in the Planck Epoch. Every atom in your body, every thought you have ever had, every moment of experience you have ever lived, is a downstream consequence of whatever happened in a region of the universe smaller than a Planck length, at a time earlier than a Planck time, in conditions that no physics we possess can describe. You are, in a very literal sense, the product of the Planck Epoch. You exist on the far side of the wall. And the wall is not just a cosmological abstraction. It is the foundation on which everything you are was built, a foundation we have not seen, cannot see, and may never see. Here is the honest, uncomfortable, extraordinary position that physics has arrived at after a century of extraordinary progress. We have a detailed, accurate, observationally grounded description of the universe from about 1 second after the Big Bang to the present day, roughly 13.8 billion years of cosmic history, described with remarkable fidelity. We have solid theoretical extensions that carry us back with decreasing certainty to about 10 to the negative 35 seconds. And then there is a wall that our best theories both crash into simultaneously, a wall that defines the scale at which space-time itself may cease to be smooth and causal, a wall behind which the initial conditions of everything observable were set, a wall that separates what we can describe from what we cannot, what we can know from what we cannot, and possibly what exists from what does not, in a sense of exists that may itself not apply on the other side. The universe began, as far as we can tell, as a paradox, two mutually incompatible truths, both absolutely grounded, colliding at a single scale and shattering our ability to describe what was there. In the absence of a theory of quantum gravity, a theory that does not yet fully exist, we are left with the paradox unresolved. We are left standing at the wall. And the most honest, the most scientifically rigorous, the most intellectually serious thing we can say about what is on the other side is, we do not know. Perhaps a previous state of the universe, transformed by a quantum bounce. Perhaps nothing at all, in a sense of nothing that does not mean empty space, but genuinely no space-time. Perhaps a smooth, no-boundary origin where the time direction fades into a spatial direction like the South Pole. Perhaps a bubble in an eternally inflating background. Perhaps something we have not yet conceived. The universe is not hiding the answer out of cruelty. It is hiding it, if hiding is even the right word, because the question touches the very deepest structure of what exists, deeper than particles, deeper than fields, deeper than space-time itself. The wall we cannot see past is not just the boundary of our knowledge. It may be the boundary of what knowledge, as a human concept, can reach. And perhaps that is the most extraordinary thing physics has discovered in the last 100 years, not what the universe contains, but where its own description stops. The universe has a wall built into its own laws, and standing at that wall, looking back at everything that exists on this side of it, every galaxy, every star, every planet, every living thing, every thought, every moment, and knowing that all of it emerged from something on the other side that we have no description for, that is not a failure. That is the frontier. That is where the questions are so large that they exceed not just our current answers, but quite possibly our current capacity to ask them in the right way. And if history is any guide, that is exactly where the next great revolution in understanding is waiting. Whatever is on the other side of the wall, whether it is a doorway into something larger or a true edge beyond which the word beyond loses meaning, the universe, in placing that wall precisely where our two greatest theories simultaneously collapse, seems to be telling us something, not in words, in structure, in the mathematical inevitability of the Planck threshold. It is telling us that what we have found so far, extraordinary as it is not the whole story, that the deepest chapter is the one we have not yet written, and that the most important question in science, perhaps the most important question there is, remains exactly where Planck left it in 1899, staring out from behind three constants and a wall we still cannot see past.